Okay, so for this problem, we are given a rectangular barge that's 80 feet long, 30 feet wide, and 20 feet tall, and we're told that it displaces 550 long tons of salt water. So two things to notice right away. They gave us the displacement in long tons, which is traditional for kind of maritime weights. So when we're talking about ships and boats, we generally don't talk about normal tons, we talk about long tons. And the difference is 1 ton is equal to 2,000 pounds. However, 1 long ton is equal to 2,240 pounds. So you got to watch out for that when you're doing problems. Pay attention to whether they say long tons or normal tons, because that'll get you. So the second thing is that it said salt water. So the reason that's important is because the specific weights of salt water and the specific weight of fresh water are different. The specific weight of salt water is 64 pounds per foot cubed, whereas the specific weight of fresh water is 62.4 pounds per foot cubed, right? So if you were to use long tons saltwater specific weight instead of freshwater specific weight, or vice versa, your answer would be off by about 3%. So it's important to note that for this problem, we're using long tons and we're using saltwater. Okay, so then the problem asks us find the current draft of the barge and then also find out how much extra cargo the barge can carry. All right, so the first thing I always do with these Archimedes principle problems is draw a picture for it, because it will help you get in your mind which dimensions are what and which ones are changing and what's going on with the problem. So we have a rectangular barge. It's floating in salt water. And this is my attempt at a 3D drawing. Please don't judge, right? So we know that the barge is 30 feet wide. It's 80 feet long. And in total, it is 20 feet tall. And the problem is asking us for the current draft. So that draft is what height or distance is there between the water line and the bottom of our barge. All right. And then we also know that this barge is 550 long tons. Okay. Or that it displaces 550 long tons of salt water. So what that means is we have a barge and we know that it's floating. Therefore, in the vertical direction, the forces acting on it are the force of buoyancy and the force of gravity. And that's it. So if we go back to our statics, sum of the forces in the y direction is equal to 0. And that's equal to the force of buoyancy minus the force of gravity. Therefore, the force of buoyancy is equal to the force of gravity. I guess I should be consistent and use little g. Okay, so the force of buoyancy, right, by Archimedes' principle is equal to the weight of water displaced. And it tells us that 550 long tons are displaced. Therefore, the ship weighs, or the barge weighs 550 long tons. So that's kind of this process, right? You do not need to repeat this every time, but it's useful to keep in mind. And again, this is for floating objects. It's useful to keep this in mind, that remembering why we're talking about displacement of water and force of buoyancy and gravity as if they're interchangeable, because for a floating object, they should all be numerically equal to each other. Okay, so find the current draft of the barge. So anytime that we want to relate a displacement of water with some kind of dimensions on a ship, that's our clue that this is an Archimedes principle problem. So Archimedes' principle is that the force of buoyancy is equal to the specific weight of water times the volume that's displaced. So that's kind of I guess in general, it's not even the specific weight of water, it's the specific weight of the fluid. Now for us, we know that it's in salt water, right? So we can rewrite this as the specific weight of salt water, right? And then we can look at that volume displaced. So for the volume displaced, you want to look at the volume of your object that is underwater. So we'll go ahead and we'll kind of cut our ship at the water line, right? And look at what volume is that that's underwater. Okay, so we know that that's still making kind of our rectangular volume, right? So if we just had a rectangular box and we asked what is the volume, you would say that's length times width times height, right? Length, height, width. So looking at our ship, right, our volume is going to be equal to the beam, which is normally the width, times the length, which is the long part of the ship, times the draft. Now, the draft in naval architecture is given the variable T. I do not know why, that's what it is. However, it comes out really nice that when you have rectangular barges, your volume comes out as BLT, which is pretty easy to remember because it's like a sandwich. So, BLT. So we know that the force of buoyancy is equal to the specific weight of salt water times the beam times the length times the draft. And at this point, we're pretty much set to go on ahead and say that the force of buoyancy is equal to the weight of water displaced, which is 550 long tons, is equal to specific weight of salt water, so that's 64 pounds per foot cubed, times the beam, which is 30 feet, times the length, which is 80 feet, times the draft, which is what we want to find. Rearrange this, we get that the draft is equal to 550 long tons times 1 over 64 pounds per foot cubed times 1 over 30 feet times 1 over 80 feet. Right, so if we were to go in through and look at our units, we have 2 sets of feet on the bottom. So that's going to cancel this down to just feet to the first, which is good because we want our answer to be in feet. But then we have long tons and pounds, right? So we need to cancel our units. So we know that 2,240 pounds is equal to 1 long ton. Long tons cancel long tons. Pounds cancels pounds. And we're left with just feet, which is what we want. Plug that in all into our calculator, and we get that the draft is equal to 8.02 feet. Awesome. Part 1, current draft, done. So the next part is asking us how much extra cargo can the barge carry before it sinks, right? So if we look at our barge, we can see that it's already got an 8-foot draft. So that means there's 12 feet of it that's still above water. So as we add extra boxes to our barge, it's going to sink more, right? You all know this. You have all seen something like this happen in real life. So it's going to start sinking and going down, which is what we want. Because essentially what we want to find is when our barge is completely underwater. Now again, hey, it still has that 30-foot beam, but I'm going to dispense with doing 3D drawings because they always look pretty bad. However, now that it's completely submerged, the entire 20-foot height of the barge is underwater, and it's still 80 feet long. So looking at this, we know from Archimedes' principle that the force of buoyancy is equal to the specific weight of salt water times the beam times the length times the draft. All right, and from our statics, we know that the force of buoyancy is equal to the weight of the ship. So this is also equal to the force of gravity is equal to specific weight of salt water times beam, length, draft. So we can go ahead and plug in 64 pounds per foot cubed times 30 feet times 80 feet times 20 feet, because again, barge completely underwater. And we get, not quite yet, and then because we have the initial weight of the ship is 550 long tons, we're going to convert this to long tons as well, so that we can compare those two numbers. So 2,240 pounds per 1 long ton. If we do that, we get that the weight of the ship when it's completely submerged is 1,371 long tons. Final 1,371 long tons. And again, that's the final after we've stacked all the boxes on top of it that sank it. All right, so if initially it was 550 long tons and in the end it was 1,371 long tons, then the weight of the cargo we added is just the difference between those. So weight of cargo is going to be equal to 1,371 long tons minus 550 long tons. And if we do that, we get 821 long tons. And if we were to go ahead and look at our picture, right, that would make sense because we knew that this barge shape was 550 long tons. Boom. Right? And then these boxes are the extra 821 long tons for the total weight of 1371.